Okay, so now that we have learned about what power and efficiency are, we're going to solve some problems doing that. Now, I want to give you a procedure for analysis, and then we're going to jump straight into our first example problem. So first off, you're going to find the resultant external force acting on the body, which is causing its motion. You're probably going to need to draw a free body diagram. That's just per the course. Pretty much everything in your procedure is going to require a free body diagram. Then you're going to determine the velocity of the point of the body at which the force is applied. You're like, wait, well, isn't the body moving at the same velocity? I don't know. If I rotate this, is every single part of that have the same velocity? Answer, no. Now, we haven't gotten there yet, but that's going to be something you're going to have to think about in the future. Energy methods like our principle of work and energy might be very helpful on these kind of points. And kinematics, you're never getting rid of them. End of the semester, you will still be using kinematics. The very last assessment, very last quiz, you'll still need kinematics. So don't forget it. Then you're going to use that equation for power, which is simply force times velocity times cosine of the angle between them. Remember, power is a scalar. Or you might use this differential. You can take the derivative of work with respect to time and maybe find power in that way. There's various ways you could do it. And finally, if you know the mechanical efficiency, it might be helpful to figure out what the power input was or what the power output should be based on a particular power input. Okay, so free body diagram, energies or kinematics. Multiply your force and velocity together or take a derivative. And finally, if you still can't figure it out, fall back on mechanical efficiency. If you still can't solve the problem, you should probably send me an email. Let's talk. But right now, let's try out an example. And if you want to, you can go ahead and pause and try this on your own. Otherwise, just keep on listening. It's our very first example, and I want to make sure you actually know how you're doing this. So what we have here is a 50-kilogram block, and it's hoisted by the pulley system in motor M. That's hoisting it. That block is moving, and it's moving up. At this instant, point P on the cable has a velocity of 12 meters per second, which is increasing at a rate of 6 meters per second squared. And what do we want to find? Well, we want to find the power supplied to the motor at this instant. Ooh, interesting. Power supplied to the motor at this instant. Well, what's our plan? Well, we should remember that power is equal to force times velocity. And luckily for me, I know what the velocity is. It's 12 meters per second. But I don't know what the tension in that cable is. So that's still kind of leaving me hanging. So we're probably going to have to figure that out. So what we want to do is we want to draw a free body diagram of the block. We're trying to figure out how fast it's going to move. Then we're going to use our equations of motion to determine the cable tension. And then it's pretty simple to figure out what the power is from there. Okay, so let's move forward. First off, we're going to have to solve this. You're like, I thought we were done with cables. We aren't done with cables. These are going to be around for a while too. So you need to define position coordinates. I could do it from several places. The one that makes the most sense is from up here, because my distance to this point P and my distance to the point A are both easy to solve for in that regard. And then I make a total length equation. Well, the length is going to be equal to SP plus 2SA. I don't care about this section right here. And then if I take a double derivative, well, I'll get to the acceleration, where the acceleration of P is going to be equal to half the acceleration of A. Sorry, twice the acceleration of A. So, if my acceleration of point P is 6 meters per second squared, my acceleration of point A is going to be 3 meters per second squared, and it's going to be going up because I defined my positive direction as down. This is negative. Okay, so total length equation. I take derivatives twice to get here, and then I plug in what I know. Now that is enough to figure out the force in the cable, because I already know what the weight of that block is, and it's 50 times 9.81 meters per second squared newtons. I know that there's two T pulling it up. And that tension is enough to accelerate it. It's not just constant. This isn't statics, it's dynamics. So it's going to cause an acceleration. So from that, I start solving some equations. So my sum of the force in the y direction is going to be equal to the block A's mass times its acceleration. And then if I look at this, well, I've got the tension pulling it up minus its weight pulling it down is equal to the block times its acceleration. So the tension would be 320.3 newtons. Now, the power applied by the motor is going to be the product of the force applied to the cable and the velocity of the cable. So it's going to be 3,844 watts. That's just force times velocity. In this case, they were in the same direction, so all is well. And we're done. Wait, are we? Because I didn't actually ask for the power supplied by the motor to pull things. I wanted this power supplied to the motor, not the power supplied by the motor. Key word here, by to. That's the power going in. This is the power going out of the motor. The power going in the motor is obviously going to be more than this because our motor was not perfectly efficient. It was about 80% efficient. So I have to divide by that fractional efficiency. Divide. I want to get the power input. This equation right here, I'm just going to say right now, it's probably a good one to write down. So in doing that, I see that I would actually have to supply 4.8 kilowatts, or about 4,800 watts, in order to do that much, or sorry, to output that much power. So that is the answer. That's all we need right now. So please, please, please remember, efficiency is going to be in most of these problems, and the power going into your motor, or the energy going into your motor, is always less than what comes out of it, because it's not perfectly efficient. So, thanks for watching. I hope this helped you, and I'll see you all next time. Bye-bye.